and thank you very much for this opportunity. I'm Hasan. I'm from University of Nebraska-Lincoln. The topic of my talk will be the generalizability of deep contextual models. So when I say deep contextual models, I would refer to the language models um, based on deep neural networks. And the central question that I'm trying to understand whether these models are truly generalizable or not. For the purpose of this paper, I've only focused on BERT type models. So these are encoder-only transformer models, but you also know that there are decoder-only models, for instance, ChatGPT. I'm not focusing on that. I'm just interested on encoder-only BERT type deep models. Now, these models are very powerful, as you know, and these models achieve state-of-the-art results on benchmark data sets, which is great. But what I wanted to know, what I wanted to understand is whether these models are equally good at real-world data sets or real-world problems. Can we apply these models to real-world scenarios and get similar impressive results or not? That was my question. And to make this investigation interesting, I focused on a couple of issues. What happens when I have a real-world data set where some of the labels are noisy? The labeling is done in an unreliable manner. What happens if I use a data set for testing which is out of distribution? And finally, how do these models really interact with scenarios or data sets where language patterns are shifting or dynamic? So three key questions. What happens when the labeling is done in a noisy or unreliable manner? What happens when data is out of distribution? And what happens when the narrative in the data set changes over time? And to ground my investigation in a real world scenario, I focused on this COVID misinformation problems. During the time of COVID, people would post different types of things on social media, including misinformation. And at that time, people have collected curated some data sets, which is nice for us to make this investigation. And if we look at those data sets, we will see that the labeling in some of those data sets for some misinformation category was not really reliable. So what happens when we include that data that has unreliable or non-reliable labeling in it? The second aspect in those COVID data set was that the narratives, or if you like, the misinformation types can change, can vary across different geographic regions. For example, the type of misinformation in Mongolia could be different from the type of misinformation from United States. So if you train a model based on the data from United States, and then can you apply that model to detect misinformation in a different part of the world or not? That was the other question. And the final question was this: what if we just focus on one geographic region, let's say United States, collect data, train model, and then apply that model to detect misinformation at a different time? So if we train a model from data obtained from the period of January to April, can that model be applied in the same year during the month of, let's say, July or December or not? So again, three interesting questions. What happens if my data set contains a category that is unreliable because the labeling was not done accurately, which is quite typical or was quite typical during the time of COVID. People used to do that manually. They didn't have a lot of domain knowledge. So they ended up assigning incorrect labels. That was the first question. The second question was, what happens when the narrative changes across different geographic locations? And also what happens when the narrative changes over time? So based on these three interesting questions, we created this research. The data set that we used for this research was pretty standard. It came from Princeton University. It contains more than 5,000 COVID misinformation stories. And the impressive part is that it came from more than 80 countries, 35 languages. But then in my research, I focused on just the English misinformation stories. So as a consequence, my data set was much smaller, containing 1,200 plus samples. And there are three types of misinformation that I considered here, which includes false reporting, conspiracy, and fake remedy. So 1,200 plus samples. It's a three-class classification problem: false reporting, conspiracy, and fake remedy. The false reporting class had more than 75% of the instances. So the data set was quite skewed. For the investigation, I utilized a couple of different models. So first of all, my interest was understanding whether deep contextual models are at all generalizable or not. So for the deep contextual category, I focused on BERT and some of the domain-specific variants of BERT. For instance, they're health-focused or health data-based BERT variants, for instance, SciBERT, bioclinical BERT, and COVID Twitter BERT, which was very close to the kind of problem that I wanted to investigate. So these are all so-called deep contextual models. And then I compared the deep contextual models with shallow non-contextual models. So shallow non-contextual models, these are non-contextual in a sense that they do not have a lot of capacity to understand the syntax, the semantics, and the context of the data. And two models of interest that I considered was word-to-vec, shallow MLP type neural network, fast text, a statistical kind of a model. So essentially what I did with word-to-vec and fast text, I used these models to basically generate the embeddings for the samples that I had. So each COVID misinformation story, I passed them through these models. It generated the embeddings. And then using those embeddings, I trained a neural network for solving the classification problem. For instance, I used convolutional neural network. So in summary, I focused on two different types of models, the deep models and shallow models. Under the deep model, I had domain-specific variants of it. Now let's turn to the deep contextual models for a minute. BERT. So some of you or most of you would know that BERT is a language model because it was trained with a technique we call masked language modeling that essentially allowed it to understand the syntax, the semantics, and the context of the data. The two variants of BERT that I used was BERT base, 110 million parameters, and BERT large, 340 million parameters. And these BERT variants are trained using general purpose data sets, book corpus, English Wikipedia, right? As a consequence of this general purpose database training, the kind of BERT models that we got are domain agnostic BERT models, which means these BERT models, they do not necessarily know the context of the COVID narratives, the COVID scenario. So they're domain agnostic. And later on, you will see that we also have domain-specific models. Some models that are trained using COVID data. In the last slide, you saw one of those models, COVID Twitter BERT. So I had some deep contextual models which are agnostic to the domain. They don't know about the COVID. And then there are models that know about health-related issues, know about COVID, and so on. So the BART models are used in two different ways for transfer learning. The first way, I simply added a classification layer and did the fine-tuning for the three-class misinformation detection problem. Simple, straightforward fine-tuning. The second approach was I extracted features from the BERT, either from the final layer or from the classification layer, and then use those embeddings to train another neural network, a convolutional neural network. So fine-tuning or feature extraction, feature-based learning, two ways of using BERT. Then I talked about the data set. I talked about the different models that I used. Now let's talk about the different studies that I designed. There are four specific studies that was of interest to me. So study 1 and 2, I compared what happens when my training data includes an unreliable category. So I created a category of samples where the label was simple unverified. Okay, I don't know the label, so I'm not sure about the label, and I still want to include that class in my data set, right? So I compared two models, one model that was trained without the unreliable category and another model that was trained with the unreliable category. And then I wanted to see what's the impact of the inclusion of the unreliable category. Study number 3, which was interesting, I focused on the generalizability question, really. I wanted to understand what happens when I train a model on my existing data from one particular geographic location and then test it on a data from a different geographic location. So it's out of distribution, OOD data from a different geographic location. The final study, what happens if I train my data from one location at a particular point of time and then test that model from the data from the same area, but from a different point of time? So temporal variation. So in summary, the 3 different investigations that I ran, investigation number 1, study 1 and 2, that was about what happens when data has noise, a noisy category. Dimension 2, study 3, what happens when the data was trained from one location, tested on another location. The final study, there's a typo here, it should be study 4. It's about what happens when I try to apply the model at a different time in the future. Okay. So again, dimension number 1, noisy categories. I included an unverified category. So I took some samples and then I just replaced their label with the word unverified. It's a new category. Okay. So study number 1, 3 classes accurately labeled. And study number 2, there are 4 classes. A new class was added with this unverified category. And I compared these 2 different experiments, and I wanted to know what happens when the labeler did not have a good understanding of the domain. I'm not sure about this misinformation type. What do I do, right? I'm manually labeling the data set. So when a labeler doesn't understand the domain very well, what does that person do? That person injects noise in the data set, in the class types. So what's the impact of that? That was my question for the study 1 and study 2. So study 1 was control, no unreliable category. Study 2 contains an unreliable category. So that's about noise. The second dimension was geographic shift. I trained a model using data from English-speaking countries, right? And tested it on non-English speaking countries. Although the messages were all English, but it's just that the training messages came from English-speaking countries and the test messages from non-English speaking countries. So I wanted to understand what happens when I try to apply the model on a different location. Does the model generalize well or not? Okay. And the final study is temporal shift. So I trained a model using the data from January to April. Okay, and then I tested it on 4 different subsets. The first subset was from May to June, second subset from July to August, third subset September to October, and the fourth subset was November to December. It's the same year, but it's just that they're progressively far away from the training duration, training period, which was between January to April. Again, I wanted to understand what's the impact of the temporal variation on the model's capacity to generalize, right? So I talked about the data set. I explained that the kind of models that I wanted to use and the 4 different studies that I designed. Now let's look at the results. First of all, the noisy scenario. On the left, you're looking at the result from study 1, where I did not have any unreliable category, no noise in the data set. And on the right, study number 2 that contains the unreliable category. Okay, so I compared different types of models. The purple colored bar charts represent shallow models, and the yellow colored bar charts represent deep models, both domain agnostic and domain specific. So purple, shallow, yellow, deep. It's a 3-class classification problem. So inside each bar, you will see the F1 score for each of these classes. The height of the bar is the average accuracy, and on the very top, you will see the standard deviation. So when we look at the result from study 1, we notice that almost all of these models, or I think, yeah, all these models achieved more than 90% classification accuracy. And they did pretty well across all 3 classes, right? Now let's compare that with study number 2, where I had, so study number 2 was a 4-class classification problem. We had an extra class with unverified labels. And notice that the model was pretty confused, okay? The performance, the average accuracy dropped by 20 percentage point because of this noise in the data. And even though I created this noise artificially or synthetically, but it is not unnatural for the kind of the data set that I used. The COVID data set had noises in it in terms of labeling. And one interesting insight that I obtained from this experiment, study 1 and study 2 comparison, that the shallow word-to-vec model did actually slightly better than the deep model. So just because of the fact that the model is deeper doesn't necessarily mean that it would do better. Even the shallow models could perform well. And this kind of challenges the assumption about the generalizability of deep models, deep contextual models. But that was study 1 and 2 on the presence of noise in the data set. Now let's turn to the third study, which was about the geographic shift in the data distribution. Again, the purple bars are shallow models, non-contextual, and the yellow bars are deep models, they're contextual. And notice that all of these models achieve above 85% test accuracy, which is not too bad. But what is problematic here, if you look at the score for F1 score for the second class, one of those misinformation class, all of these models had issue, 0 F1 score. All of them did poorly. So even though the average accuracy was good, but the model had difficulty generalizing into the non-English speaking countries. The final study, it's about temporal shift. The models were trained from the data obtained from January to April and was tested on 4 different subsets at 4 different times in the future. Starting with May and June, you're looking at the average accuracy, and then July, August, a slight decrease in average accuracy for some models. But one thing to notice is that there is not much of a difference in terms of the performance of the deep models and the shallow models. They're doing more or less similarly. Now we progress farther in the future, September, October. You see that the performance of these models, both contextual and non-contextual, they decreased, right, significantly. Farther down in the future, November, December, more decrease in the performance, right? One thing to notice here is that if you look at some of the domain-specific models, DS, Cybert, as you can see here, or COVID Twitter, CT, COVID Twitter bird. Among the deep model category, the COVID Twitter bird did well, 70% test accuracy, slightly better than the large bird. But in general, overall, none of these models did well. So if we compare from very high level, if you compare the key findings of these three, the last two studies, the geographic shift and temporal shift, this is what we see. So let's look at the geographic shift. It suggests that even though there was geographic variation, the models achieved at the level of 80% accuracy. But do remember that all of these models did extremely poorly on one of the misinformation class. So that tells something. In terms of the temporal variation, so when we tested the model on the future data, if the future is not too distant, for instance, May to August, we did notice that the performance was slightly below 80%. But when you move farther away into the future, for instance, September to December, notice that the performance is significantly low, below 70%. So by comparing the temporal variation across two different times in the future, May, August, and September to December, you see as you move away into the future, the models keep on doing poorly, especially on the minority classes. Okay. So that's kind of our key insight from the temporal variation out of distribution experiments, that as you move farther away from the current time, the model keep on doing poorly in terms of generalization. The only model that did slightly better was COVID Twitter BERT, some resilience, but then again, you have to understand that this bird, specific bird variant, was trained on COVID Twitter data. That's why it did slightly better. It's not ideal. 70% is not ideal, especially for misinformation detection. So I've explained to you the results from 4 studies, and we have seen that these deep contextual models have real difficulty generalizing over time, generalizing across different geographic locations, and they're prone to the performance degrades due to the noise in the data set. Now let's try to understand why, right? Why do these models fail in some of these cases? The first key observation, the key insight that I can share with you from my study, based on just BERT, is that these models are trained on the data set using this masked language technique, modeling technique. And as a consequence of that, these models have a very strong prior, language prior. They learn the typical model of the training data set that was used to pre-train the model. And it was difficult during the transfer learning process to break that strong prior. Maybe one way to go beyond this or maybe mitigate some of this issue is to use more data, which unfortunately I did not have. Static understanding. These models, deep contextual models, BERT type models, they're trained using static data, right? But think about the COVID scenario. It was evolving too fast. So if you need an AI that would help you to navigate through a dynamic scenario, then you have to encounter this issue of this static source data-based training. And also finally, we have seen that even if you train a model using domain-specific data, so you're interested in COVID misinformation detection, you collected COVID data, tweet data, you trained a COVID model, BERT model using the COVID data, still it was not doing well when it comes to the future data, right? Because the COVID Twitter BERT model, which you should know that it was trained using the data obtained from January to April, pre-trained, right? Which we fine-tuned, of course, with our data, but still, it didn't generalize well. So the key insight that from this analysis, the analytic part that we can draw is that these models have difficulty understanding the language change. They're not very dynamic. And this is a critical requirement for deploying these models in any real-world applications. So that's why we need to rethink about model selection. Deep contextual models don't necessarily will do well in every scenarios. What we have seen in our study is that when what we did, we took this word-to-vec model and we trained it using our COVID data, right? When we trained the model using the COVID data, the model, even though it was shallow model, just single layer based MLP, it learned the context of the data from limited examples that we had, 1200 plus, right? And then from that domain specific model that we created from our own data, shallow model, we extracted the embeddings. And using those embeddings, we trained CNN. And that CNN did better than the BERT fine-tuned models. So which means that it's not necessarily true that if the model is bigger, larger, deeper, then it would do better for the particular application that you're interested in. We also need to be very careful about the limitation of these models in terms of their understanding of the temporal shift and the geographic shift and their resilience to that before we deploy these models or tailor a model for critical applications. So we certainly need new techniques especially for handling noisy labels. And this is another, it's kind of a blind spot that we need to address for critical applications. We should not be blind to the fact that the data that we will be using for fine-tuning or adapting the model, they're all clean. They are never clean, okay? And the labelers, we rely on human labelers, and human labelers often, unless they're trained, they're often they often lack the domain knowledge, and that kind of injects their bias, noise in the data set, and that would degrade the model's performance. So how do we address that? That's a key question that emerge from this analysis. And finally, it's not so we are overhyped about the language models, right? Language models are great and so on and so forth. But we also need to understand that language modeling is one thing, and the capacity to understand the evolving language pattern is a different thing. Because when we train a language model, we do it on a static data set. This is an expensive process, right? So, but for a pandemic like COVID-19, the narrative, the phrases, the wordings, the expressions, they can change over time dynamically. And we don't know how would we cope with that kind of a change. So it's not just about language modeling. The deeper question is, how do we understand, how do we make those models to understand the evolving pattern in the language? Which finally leads us to the conclusion of this talk, which is we need to develop models for understanding language, but more importantly, we want the model to understand the changes in the language, not just its grammar, not just its syntax, not just its semantics, not just its context, but more than that. Context changes. The change is the key word. And how do we achieve that? That is the question. Benchmark data sets are good, very useful, But then again, we have to understand that they're primarily IID data set. So the statistical distribution of the benchmark data sets are not fundamentally very different from the distribution in the training data set. But in real life scenarios, especially the scenarios that are heavily dynamic and time critical, we may not have the luxury to expect the same kind of distribution that we had in the training data set. So in summary, this research would push forward uh, the need for developing ideas for creating models, creating AI systems that can understand the change, not just the language. Well, that's it. Thanks to my students, my sponsors, and especially thank you very much, the organizer of this conference.